Good morning, everyone. I am Dr. Kushal Roy from the Department of Electronics and Communication Engineering at the Institute of Technology. And today in this session, we will be discussing delay generation techniques in 8085 microprocessor. Starting with now, the first thing which is required to be known by all that how these delays are generated, requirement of delay generation, what are the general methods of generating the delay, and simple examples of delay generation along with the calculations. Calculations means how we can implement those delays with exact time values. Now, now defining the delay. Delay loop is a loop which is used to delay the program execution or increase the execution time. To keep, for example, now the question arises, the most important attribute of the microprocessor is its speed. If the speed is up to the mark, then why we deliberately want to reduce the execution time or execute or implement some delay. Now, say for example, to keep a display for some types on any 7-segment display, which is microprocessor based, if the display goes at the speed of the execution time of a processor which is very large, in that case nothing will be visible and we will not be able to, or our eyes will not be able to interpret anything. This is the main reason why delays are being introduced, though there are other reasons also. Okay. Now there are few methods of generating a delay. The first one is using NOP instruction, that is no operation. Now this no operation instruction is a single byte instruction. This instruction is not sufficient enough for generating the delay of the order which I am trying to explain. Now there is the second way, which is by using 8-bit register as a counter. There is another way, which is by using a 16-bit register as a counter. Now these ways go from top to bottom based upon the time required, or the delay time which is required to be generated. We will be seeing it in our next slide. Okay. Now, before going for this delay generation process, I would like to tell my students and the viewers that from the prerequisites of microprocessor, we know that each instruction goes through a series of, or comprises of a series of cycles, machine cycles, like opcode fetch, memory read, memory write, sometimes IO read, sometimes IO write also. Okay. And knowing the combination of these cycles, the three most important things about the instructions which are used in the delay are how many byte instruction is used, what are the machine cycles in those instructions, and finally the most important thing is the T state. How many T states are involved in execution of that particular instruction. Now this is a very simple delay loop, very simple, which is using simple 8-bit register as a counter. Now if you just have a glance at this small 3-line program segment, this is not a program, it's a segment program, or you can say a subroutine also. So here in register C, I am moving a number, 8-bit number, hex number, which is FF. In decimal, this is 255. Then I am decrementing it using DCR instruction. Then I am using a conditional jump statement, which is doing what? If the condition is not satisfied, in that case, it is again decrementing the value and checking. So this process goes on how many times? FF times, that is 255 times. So basically by using 2 loop instruction and 3 loop segment of a program, we are able to generate a delay. Okay, now we will see. I told you in the previous slides that the most important thing is to understand the number of T states which are there in a particular instruction. Now for MVI instruction, it's a 2-byte instruction. It has 2 machine cycles and 7 T states. For DCR instruction, it is 1 machine cycle and 40 state. Now coming to the conditional jump statement. The conditional jump, here we have used jump on no zero. So this conditional jump has basically 10 t states. Okay. For those conditions when the condition is not satisfied and the loop is working. The moment the condition is satisfied and the control comes down from this instruction, what happens? The number of t states gets reduced to 7. So this fundamental one has to know before proceeding for either generating any type of delay or calculating how much delay is there. Now, how to do this calculation? Now see, what is the delay? Just let me go back and try to explain. This is the instruction MVIC which is outside the loop and it will be executed only once. The instruction DCRC and jump on no zero. This is the actual loop which will be executed again and again and again. How many times? For this case, 255 times. So basically, we have to divide this entire segment into two parts. One is the part which is outside the loop, and one is the part which is inside the loop. So here we have seen this instruction has 7 t states. First of all, let us count the number of t states within the loop. It is 10 plus 4, 14. And these 14 t states will be repeated how many times? It will be repeated ff number of times. Ff in hex, that is 255 times. And when the last iteration comes, what will happen? This 10 will be reduced to 7. That means if I keep on doing my calculations with 10 t states, I have to subtract 3 at the end. This is what I have done. See, the total delay, T delay, TO is the delay outside the loop and TL is the delay of the loop. That means the loop itself. Now TO is the sum of both these two. Now here, let us assume that the microprocessor's working frequency is 2 MHz. In that case, 14 T states will be repeated 255 times, which is inside the loop, minus 3, because in the last iteration, jump on no zero condition will be satisfied and it will have 7 T states. So we have accidentally added 3 T states, which I am subtracting. So 3567 T states are there. Okay. From these 3565 T states, 14 T states, I have already mentioned this, so I'm not covering it again. Now there is one which is outside the loop, and that is the MVI instruction. This will be executed only once. In that case, I have to add these 7 T states to the actual result. So total for these 3 instruction segment, I am getting 7 plus 3, 5, 6, 7 T states. And these T states will generate a delay of how much? Since the frequency is 2 MHz, 1 T state is 1 clock pulse, which is 1 by 2 MHz, which is 5.5 microsecond. So entire delay time which is generated is 1.787 milliseconds. Now using a single register, one can repeat a maximum of 255 times. This I have told you. Maximum of 255 times, because one register is 8-bit in capacity and maximum it can hold FF in hexadecimal number system. So by this, many people will argue that this delay is very small. See, the delay generated is of the order of 1.787 milliseconds. I want to increase it. What is the way of doing it? No, sir. Now, one can go for a registered pair, which is our second segment of this discussion. We can go for 16-bit registered pair. But there is a problem. Here, I have used DCR instruction to decrement the register. But if I take a register pair, I have to use the instructions INX and DCX. And unfortunately, no flag is modified or affected by this DCX and INX instructions. Now, if the flag is not modified, in that case, directly putting a 16-bit number in a registered pair, decrementing it using DCX instruction, and then directly using jump is not going to work, because how the jump statement is going to work if the flags are not modified? It is not going to check the flags. So in that case, we will be using a trick, a small trick. Let us see. Now this is an example of registered pair count. Here, if you see the first instruction, LXIB 1000H, I have stored 1000H in the BC register pair, and I have decremented it. But I have not used the jump instruction directly. What I have done is I have moved the lower byte to the accumulator using move A, C, and then I have logically ORed it with the accumulator. Now what happens? We all know that in the OR operation, until and unless both the entities are 0, in that case output will not be 0. Okay. Now when we are doing this OR operation or any logical operation, maybe AND also, OR also, these operations do modify the flag, they affect the flag. In that case, I can use the jump or conditional jump instruction. Now, just I am giving an overview of the T states. LXI instruction has 3 machine cycles and 10 T states. It's a 3-byte instruction. DCXB has 6 T states. Move instruction 4 or instruction 1 machine cycle 4 T states. And again jump, I have told previously also, 10 T states when the condition is not satisfied and 7 T states when the condition is satisfied. In that case, again the same procedure. If I go for 10, then I have to subtract 3 for the last iteration. Now, we will be using the same formula. Let us see the previous slide. This is 1000 hexadecimal number, which is equivalent to 4096 in decimal. So this count is for 4096. Now, this is outside the loop. This is inside the loop. This is inside the loop. This instruction is inside the loop. This instruction. So total how many T states? 10, 14, 24. 24 T states are inside the loop. 10 T state is outside. 24 outside the loop, 10 T states. Inside the loop, 24 cross 4096. That is the count. Minus 3. So this is 98,301 T states inside the loop. And what about T states outside the loop? 10. We have to add this. And this will give you a figure 98,300 and I think 11. Okay. 311 T states. Now, if we again consider that the clock frequency is 2 megahertz, it is 0.5 millisecond per T state. Okay. In that case, the total generated delay is 49.155 milliseconds. So, just a matter of comparison, if you have paid attention in the previous part when we have used a single register delay or 8-bit delay, okay, in that case the delay was very small. Now we have been able to increase the delay to quite an extent. It's 49.155 milliseconds, but still there may be a necessity to increase the amount of delay. Now how to do it? Are there other ways? Yes, there are ways. Now what is a nested loop? Nested loop is nothing but a loop inside a loop. I hope people have this concept of nested loop. It is a loop inside a loop. Okay. In order to increase the number of times the iteration goes. Now here, how do we plan a nested loop? We initialize second loop, then we write the body of the second loop. Initialize the inside loop, then we design the body of the loop. We update the count, like we decrement it, okay. And then in the final, is it the final count? Our requirement is 0. Has it come down to 0? If no, then again it goes back to the loop. If it is yes, then we update the outside count. Okay, we decrement it. Okay, then again we check if the answer is coming out to be yes or the loop has ended, the count has ended. In that case, we stop it. Else, we again move to the body of loop 2. So this is a loop inside a loop. What is the purpose? To increase the number of iterations or increase the delay. Now, here is a very simple example of this. I have taken the first loop in a count in register B, 8-bit count. Let us start with 8-bit count, which is 10H, that is 16. Then we have taken another register C, which is having FF, that is 255, the maximum possible number, fixed number. Now I am decrementing the register C and I am checking whether C is 0 or not. If not, what I am doing, I am again decrementing it. So for each value of B which is decremented, there will be 255 times this loop is one. And once this 255 times iteration is over, B value will be decremented. Okay. And now what is going to happen? We will check whether this is 0. Obviously, for first time it will not be 0. So it is again going to put FF in C register. So again, for each value, this is going to work. How many times? This is going to work 255 times. Okay. Now, briefly, let me say count the number of T states. Okay. MVI instruction has 70 states. NVI again 70 states. DCRC 40 states. Jump on no 0 10 T states. Decrement B 40 states. And jump again the same thing 10 T states. And for the last iteration, this jump as well as this jump. Okay. For the last iteration, when the condition is satisfied, there will be 70 states. So again we have to do this minus. Let us see. We will start with the inside loop. Please. This is my inside loop. DCRC jump on no 0 to loop 1. And for this loop, this instruction is outside the loop. That means this instruction will take place once, followed by 255 these two. Okay. Now, let us see for the inner loop inside. One instruction is MBIC, which is outside. It will be executed only once. So this is going to have 70 states. And for the loop, see, for the loop, 4 T states, 10 T states. That means total 14 T states. Total 14 T states. How many times? FF times, that is 255 times. And minus 3. Don't forget the last iteration. Okay. These are the number of T states. Okay. Now, but this is not complete because there is one instruction which is having 70 states outside this inner loop. So we will add this up and total will be 3574 T states. Till now, this is for the inner. Now coming to the outer loop. The instruction was MBIB 10H. 10 means 16 in decimal. So 16 times 255 is going to be iterated. Now 16 into 14 plus 3574 minus 3. Where did it come from? 35674. Okay. 14 plus 3574 minus 3 for the last jump. So this is going to be the number of T states 57,405. Okay. But there is one more instruction which is outside the first loop. That's outer loop. That is having 7 T states. So add it up. Total delay will come out to be 57412. And again the same thing. Let us say that the processor has a clock frequency of 2 megahertz. In that case, for one clock period, for one T state, the time will be 0.5 microsecond. So what is the total time for this many T states? It is 28.706 milliseconds. Now, there is a point where this comparison needs to be done. Okay, we have used a nested loop with only 8-bit counter, and that 8-bit counter is going to provide me 28.706 milliseconds. But if you compare with a single non-nested single 8-bit counter uh, delay loop, in that case it was far less. So this nested loop is one of the best way of increasing the delay. Now some people might say, I want more than this. So what is to be done? So if you want more than this, there are other ways which I will not be taking place today because that is going to be a little bit lengthier. So what are the different ways? You can use 16-bit loop, 16-bit counter also in nested form. Okay, a 16-bit counter in nested form is going to provide even higher delays. Okay, and no operation instruction is already available with us, but this no operation instruction does not provide a very good amount of delay. Okay, and it makes the program lengthy also. So this is not a very preferred method in microprocessors. Okay, now let us go for a practical example, which at the end I will be leaving to you for solving it. Now, there is a scenario, a condition given. So, is it possible? We have seen micro, we have seen millisecond, okay, we have seen 47, 48 millisecond delay also. Now, is it possible for a practical 8085 microprocessor to give us a delay of order seconds, say 0.25 seconds, with a clock frequency of 5 megahertz? Clock frequency of 5 megahertz means the working frequency or inner frequency will be, inside frequency will be half. That is, it will be 2.5 megahertz. So one T state will be of 0.4 microseconds. The number of T states required, yes. How many T states are required to generate this much 0.25 second? Real time is 0.25 second. Time of one T state is 0.4 microsecond. So it is almost 1 million, that is 10 lakhs. So 10 lakh T states we have to generate. So this is a simple hint, you can say, it's a simple mathematics. Okay. The same thing I have used, which I have done in registered pair or 16-bit counter delay system. In this, I have not specified the value of count. Now, I would like to request my students and my listeners to find out the value of count so that the delay is 0.25 microsecond by the same way by which we have done in the calculations shown. Okay. So, by this, I would like to end this session. Thank you very much for listening and see you soon. Thank you.